Lesson: Reinforcement Learning Concepts. Reinforcement learning is a pivotal area within artificial intelligence that focuses on how agents should take actions in an environment to maximize cumulative reward. It is distinct from supervised and unsupervised learning paradigms, primarily because it does not rely on labeled input-output pairs or inherent structure in the input data. Instead, it involves an agent learning from the consequences of its actions by interacting with the environment. This interaction is fundamental to RL, making it a powerful tool for achieving complex tasks that require sequential decision-making and adaptability. The essence of reinforcement learning lies in the Markov decision process. An MDP is a mathematical framework used to describe an environment in RL, defined by a set of states, a set of actions, a transition function, and a reward function. The transition function dictates the probability of moving from one state to another given a specific action, while the reward function provides scalar feedback to the agent after each action. The goal of an RL agent is to learn a policy, a mapping from states to actions, that maximizes the expected sum of rewards over time. One of the most fundamental algorithms in RL is Q-learning. Q-learning is a model-free algorithm that seeks to learn the quality or Q-value of actions, which represents the expected utility of taking a given action in a given state and following the optimal policy thereafter. The Q-values are updated using the Bellman equation, which recursively relates the value of the current state-action pair to the value of future state-action pairs. This iterative process continues until the Q-values converge to their optimal values, effectively enabling the agent to make the best decisions from any given state. Another critical concept in reinforcement learning is the exploration-exploitation trade-off. An agent must balance between exploiting known actions that yield high rewards and exploring new actions that might offer higher rewards in the future. Strategies like F-greedy, where the agent chooses a random action with probability Fde and the best known action with probability 1Fbe, are commonly used to navigate this trade-off. More sophisticated strategies like upper confidence bound and Thompson sampling provide more efficient ways to balance exploration and exploitation, often leading to faster convergence to the optimal policy. Function approximation techniques, such as neural networks, have significantly advanced the field of reinforcement learning, particularly in high-dimensional state and action spaces where traditional tabular methods become infeasible. Deep Q networks, introduced by Mnit et al., leverage deep learning to approximate Q values, enabling RL agents to play complex games like Atari from raw pixel inputs. The integration of deep learning with reinforcement learning, known as deep reinforcement learning, has opened new avenues for solving problems previously deemed intractable. Policy gradient methods are another class of algorithms that have gained prominence in reinforcement learning. Unlike value-based methods like Q-learning, which estimate the value of actions, policy gradient methods directly optimize the policy. The agent's policy is typically represented as a parameterized function, and the parameters are adjusted in the direction of the gradient of expected reward with respect to the policy parameters. Methods like reinforce and actor-critic are standard approaches in this category. Actor-critic methods, in particular, combine the benefits of both value-based and policy gradient methods by using an actor to update the policy and a critic to estimate value functions, leading to more stable and efficient learning. In practical applications, reinforcement learning has shown remarkable success across various domains. One notable example is in the field of game playing, where RL algorithms have achieved superhuman performance. AlphaGo, an RL-based system developed by DeepMind, defeated the world champion in the game of Go, a feat that was considered a significant milestone in AI research. Beyond games, RL is being increasingly applied to robotics, where autonomous agents learn to perform tasks such as manipulation and navigation, often in dynamic and uncertain environments. Reinforcement learning also holds significant potential in enhancing cybersecurity. In intrusion detection systems, for instance, RL can be employed to detect and respond to threats dynamically. By learning from historical data and adapting to new attack patterns, RL-based systems can improve the accuracy and responsiveness of intrusion detection mechanisms. Additionally, RL can be used to optimize resource allocation in cybersecurity, such as dynamically adjusting firewall rules or prioritizing response efforts based on the evolving threat landscape. Despite its successes, reinforcement learning faces several challenges. One major issue is the sample efficiency, as RL algorithms often require a large number of interactions with the environment to learn effective policies. This is particularly problematic in real-world applications where obtaining such data can be impractical or costly. Techniques like experience replay, where the agent stores and reuses past experiences, and transfer learning, where knowledge from one task is transferred to another, are being explored to address this challenge. Moreover, issues related to the stability and convergence of RL algorithms, particularly in high-dimensional spaces and with continuous actions, remain active areas of research. Another critical challenge is the interpretability of RL policies. In many applications, particularly in high-stakes domains like healthcare and finance, understanding the decision-making process of an RL agent is crucial for trust and accountability. Efforts are being made to develop methods that provide insights into the learned policies, such as visualizing the agent's decision boundaries or using surrogate models to approximate and explain the policy's behavior. Ethical considerations also come to the forefront with the deployment of RL systems. The autonomous nature of RL agents and their ability to learn and adapt from their environment raise concerns about unintended consequences and the alignment of the agent's objectives with human values. Ensuring that RL systems act in a manner that is fair, transparent, and aligned with societal norms is an ongoing challenge that requires multidisciplinary efforts involving AI researchers, ethicists, and policymakers. In conclusion, reinforcement learning represents a powerful and flexible framework for developing intelligent agents capable of making sequential decisions in complex environments. Its theoretical foundations, such as the Markov decision process, Q-learning, and policy gradient methods, provide robust mechanisms for learning and adaptation. The integration of deep learning has further expanded the applicability of RL, enabling it to tackle problems in high-dimensional spaces. While challenges related to sample efficiency, interpretability, and ethical considerations persist, ongoing research and innovation continue to push the boundaries of what reinforcement learning can achieve. As the field progresses, its potential to revolutionize areas like cybersecurity, robotics, and beyond becomes increasingly evident, underscoring the importance of a comprehensive understanding of RL concepts for anyone engaged in AI research and application.